Okay, it started. Okay, so those who joined late, please don't forget to write your student number in the chat for the register. And we're going to kickstart our session. So today we're going to do time series analysis and forecasting. Because it's a very long session, so we're not going to waste more time. I might also do some of the exercises that you were going to do so that we can save more time. And then if I see that we're running out of time, I can I will also do those exercises. But if we still have enough time for every section of the concept, then I will let you do some of the exercises. Otherwise, then we will do them together. Okay, so we'll start by introducing the basic concepts of time series, then move into the types of time series, but looking more specifically at the smoothing technique, and then later on looking at the trend and analysis and seasonal effect. Then we will finish off the session by looking at how do we do forecasting by means of calculating the sum square errors and the mean average deviation model. Okay, so by the end of this session, like I said, you should be able to know about different types of time series models and the forecasting models, such as smoothing techniques, where we use the moving average or the exponential smoothing, or the trend and seasonal effect, where we use the trend analysis and the seasonal analysis to model the data. And then lastly, you should be able to know how to calculate or forecast your data as well by using the forecasting models. Okay. With time series, we are able to view the data for a period of time. So it becomes a longitudinal data where you can track the data either monthly, weekly, yearly, or so forth. And if you remember the regression analysis, where with regression, we try to predict the value. When we use the time series, we can also try and predict the next value that can occur by applying those type of a model. So it means time series can also be used as one of the forecasting model. Okay, so when we do that, then there are common approaches that you can use for this forecasting. One is the qualitative forecasting method approach. Since this is qualitative, it means you will be using your own objective. You will be using your own subjective analysis in terms of things. So you might say, oh, but in South Africa, the prices of fuel always goes up at this period of time, and you can forecast that next month, maybe because it's that month, the period of the price of oil will be, or the petrol will be this much. That is when you're using your own qualitative judgment. Also based on the historical data. Then there is the quantitative, where we use the numbers themselves to forecast or predict a value in the future. And we can use time series or we can use the casual effect. In your module, you don't have to worry about the casual one. We're going to concentrate more on the time series one, is the time series effect, where we use the historical data or the past data to predict the new data that we can have. Okay, so we're going to learn about all those things right now. So what is a time series data? Like I said, it's a longitudinal data. So it means it's numerical data obtained at a regular time or interval. And these periods can be different. It can be something that you observe every year, or it can be something that you observe on a monthly basis, or on a quarterly basis, or weekly, daily, hourly, and so forth, as long as you are able to track it over a period of time. For example, like the sales data that we have in front of us from 2000 to 2004. And we can see that in 2000, that sale, let's say these are the total sales. The sales were 7.3. And in 2004, they have increased from 7.3 to 80.2. And that's how you can use your time series data to see how things have changed over a period of time. Okay. With the data, you can plot it on a time series plot where it plots your numerical values on your vertical axis, and on your horizontal axis, you will plot the year, because we're tracking it over a period of year. Or you can plot it using the period that you choose, whether you choose monthly, daily, so you will plot it there, and you will be able to see the plot changes over a period of time. It will go up and down, or it will just go straight line. And those type of the graphs, we're going to analyze and understand them a little bit later on. So these are the time series components. So you get the trend component, like I said. If, for example, it goes up, then that it follows a linear type of a pattern, where the overall persistence is almost like it goes up straight, or it can go down, or it can just go where we say things become constant. So there is no change in terms of how over a period of time, the value stays the same. And then we get the seasonal component of the time series. So with seasonal component, it means there are regular fluctuations, but they happen at a certain period. So if I'm tracking this on a yearly basis or let's say for 12 months, and let's say I sell winter clothes or warm clothes. These days, because of the weather patterns, we know that the first 3 months of the year, we might not sell that much. But we know during the winter period, we might sell more. During December period, we might sell a little bit more. So you will see that it will show that going up on certain times and going down on a certain time, and then going up again, going down, like that. So those are seasonal, and you are able to see that if you plot your graph over a period of 12 months, it doesn't mean you must stick to the 12 months, but at least if you have 12 periods, you are able to see if your data follows any of the fluctuations or the seasonal trends that appears on there. Then we also have what we call the cyclical, which means this month it goes up, that month it goes down, next month it goes up. So the pattern are the same. So you will see there it goes up, down, up, down, up, down, up, down, like that. And that we call them the repeating swings, because there is this up and down, up and down, up and down that is happening. Unlike with the seasonal, where it happens at a certain period. It might be that only in winter that's where you see a highest peak, and then the rest of the time, the rest of the period, for example, with the winter clothes, the rest of the period they stay the same. With cyclical, it will be like if you run campaigns every second month, you will see your sales values or your sales go up on certain months because you run promotions during those months. And if you run them every second month, it means this month the sales will be normal, next month the sales will go up. Next month they go back to normal, next month it goes up. So those we call them cyclical, because then it's those repeat fluctuations that happen on a regular basis, and they are repeating. Then we have what we also call the irregular component, which these are just the errors that happen. So where there are things that you are unable to explain why things happen like that. Why do you see those peaks that just happen? And those we call them the residual fluctuation. It's based on some of the little bit of errors that might happen in your data that are not, that you cannot account for. And this is what we call the irregular component. And we're going to look at the graphs, how they look. So let's say, for example, the trend component. Remember, it's data that we take over a period of time, and this is the trend. You can see that this, even though it's fluctuating, but you can see that it goes up. So every time the data is still, it's growing and growing, it's going up. It has an upward trend. Then you also have the one where it just goes down. So the sales just goes down with the period. The whole period, where the sales just keeps on going down, and then we say this one is a downward trend. Then we also have an up-down, which like it follows like a quadratic type of, we call this a non-linear trend, but it is going up and then it tries to go down again as well. So these are the trend components. And then we also have the seasonal one. Remember the seasonal one, where it looks like a wave pattern, or it happens over a certain period of times. And this can be also be observed over a period of a year. And often we can use data from the monthly or quarterly basis. So if you use quarterlies, you will then use more than 2 years of data, so that you have 4 plus 4, then it will show you at least 8 periods of data and so forth. If it's monthly, then it's fine, because then you will see all 12 months at a time. And this will be the type of a graph that will look like this, where you can see that in this instance, the sales of some sort of a product that you sell goes up in winter and summer, and then spring and fall, everything goes back to normal. Then it goes up again. So these are what we call seasonal trends, because they happen at the same time for the same period, because all the upward trend happens in winter and in summer. Okay, then we also have those, remember I said the cyclical component, and with cyclical component, these are like long-term wave-like patterns. So how do they look? They also occur on a regular basis, and they can vary in length, because remember they just happen, and they peak to, they can, you can also often measure them from peak to peak to see what is happening, or through and through. And these are like your cyclical one. So you can see that for that one cycle, the data looked like that. And for the next cycle, it can change and look a different way. So you can just use the cycles to see. And sometimes it might be that it happens on one certain cycle of the year, where you see a dipstick, and then everything goes back to normal after that. Okay. This is your question. Which of the following component of a time series occurs over a short period, and it is repetitive in a calendar period, and by definition has a duration of less than a year? It happens on a short period and has a duration of 1 year. So let's go back to all what you know. So this is cyclical, wave-like a pattern. It happens over a long-term period. Then we have, then we have a seasonal component. Happens on a short period of time and has a wave-like patterns. And then the last one that we learned was the trend. Is data taken over a longer period of time, and you are able to see whether is it going up or down, on there's no relationship. Okay, so now let's go back to our question. So that, remember, trend, longer period. Seasonal, shorter period. Cyclical, longer period. So let's go back to our question. Which of the following components of time series occurs over a short repetitive calendar period, and by definition has a duration of less than a year? Okay, let's see. What did you say? So this is one of those that you can answer by yourself. Okay, for some reason, I can't see the, oh, see there, you have an answer as option number 5. Option 5, and that is correct. It is seasonal. It is seasonal. Question 2. 2 says, which of the following is incorrect? A cyclical occurs over a short period of time, and this almost happens, and these components are the most commonly occurring patterns in time series. Is that true? The irregular component is the leftover when the components of time series, trend, seasonal, and cyclical have been accounted for, and these are those the erratic ones. And then we have the seasonal, which is the underlying directions. Either it goes up or downwards. And the rate of change in the time series when allowance has been made for the other components. Number 4, the trend is shorter. The trend is short-term movement in a time series. Number 5, forecasting is not one of the aims of time series analysis. Which one is incorrect, or which one is correct? That's what we're looking for. To remind you of some of the time series. Cyclical is a long-term pattern. And seasonal, we know that seasonal, if I go back to seasonal, occurs over, it's observed within a year, and it's of short period of time. And we know the trend is data taken over a period, and it has an upward trend or downward trend, or it can also have a nonlinear trend. And we also have irregular component. These are the residual fluctuations that are not explained. Okay. So going back to our question. Which of the following statement is correct? Anyone? Melissa says it's 2. And Timothy also agrees that is true and that is correct. The reason why seasonality won't be correct is because it says only when allowance has been made for the other components. This statement makes seasonality not to be correct because it doesn't have to even matter whether the other ones have been made, but irregular component, it is those errors that have been accounted for. So you can take those errors or your residuals and plot them, and they will give you your trends in terms of your time series components. Okay, so and that is the basic concepts of time series. Now we're going to move into the types or the techniques of time series analysis. And we're going to start off by looking at the smoothing techniques. So with the techniques, we're going to use the moving average. So it can be a 1 year moving average, 2 year, sorry, not 1 year, 2 year moving average, or 3 year moving average, or 3 year moving average. So it means we're going to take 3 years to get, if this is a yearly figure, we take 3 years together and take the average, divide them by 2, and move to the next one, take the 3 years, divide by 2, and so forth. And that's how we're going to be creating the moving averages. Averaging all the data periods over a period and plotting them in order to see the trend that that data tells us. And the method of creating the moving average is to get all the averages, to get all an overall impression of the pattern of movement over time. And these averages will be the time series values for that chosen period and for that length. Like I said, it's going to say, if we say it's three year moving average, it means it's going to take the 3 years every time. So if the data started with 2000, and then we had 2001 and 2003, so we will start by 2003 and take the 2000, 2001, and 2003 data and average it and find the average. And then we go 2004, we will take 2000 and, oh, sorry, I don't know how to count. So it's 2000, 2001, and 2002, and 2003. So we start at 2002 and take the data from 2000 until 2002 and create an average. Then when we go to 2003, I guess you are not seeing what I'm writing. So let me change the color of the pen to red. So if we have 2000, 2001, 2002, 2003, and 2004, let's say we have 2 there, 3 there, 2 there, 4 there, and 3 there. So moving average, it means we're going to take that period because it says it will be the average of consecutive time series values. So it means if we're doing a 3 year moving average, then it means we're going to take all these years and say 2 plus 3 plus 2, 7, divide by 2. So it will be 2 plus 3 plus 2, which is 7, divide by 3. And that gives us 2.33. Then we go to 2003. We start from 2001. We take 2001, which is 3 plus 2 plus 4. And it is 9 and divide by 3, and this will be 3. Then we go to 2004, and that will be 2 plus 4, 2 plus 4 plus 3 equals 9 years. Divide by 3, it will give us 3. And you continue like that. And then you have your moving averages. And that's what moving average is about. Okay. Then we also have what we call exponential smoothing technique. With exponential smoothing technique, we take a weighted moving average of your data. And we're going to look at the different types later on. So it means we're going to weight the values, and we'll do an exercise to show you how you do the weighted averages as well. So let's first look at how we calculate the moving average. I know that I've already done that, but we'll go deep into it. So with moving average, since we are smoothing out the data so that we can see the average going up nicely, or able to track the mean over time, and also to be able to see how the data pattern looks in real actual value when we're smoothing it out. And the results will depend upon the length of period for that computing mean that we're going to create. And then with that length of time, we're going to take it and extrapolate it one period into the future so that we are able to create that forecasting. Okay, so how do we then do this? Let's look at this. So we're going to create a moving average of 5 years. So I already did an example. This is just again to refresh your mind. So if I'm doing a 5-year moving average, it means I'm going to take the first 5 years and divide by how many there are 5. Then the second one will start from year 2 and like that, and divide by 5. So this is an example of how the data, the year. So we have periods which start from year 1 until year infinity, or whatever the year they've captured it. So here we have 11 years of data of annual sales. And if we look at this data, we can see that it fluctuates there and there. There is a pattern. So every 3 months, it goes up. After every 3 months, the data goes up. So this is also what we call a seasonal trend. Or you can also look at it in terms of a linear. It can also be part of the linear because it goes up every year. The data shows as if like there is a linear trend, but this is mostly a seasonal trend because it goes up and down at certain periods of time. Okay, so if we want to see the average of this data over a period of time, then we're going to create moving average of the same data. So this is our data, remember it? So we're going to create a 5-year moving average. So it means we're going to take our first 5 years and create the moving average. So in this instance, what they remember the first I showed you, I said we will start and do moving average from year 3, and I started putting at year 3. So we're going to use the average or the mode or the median. Let's call it the median, which is the average of the middle number of the years. So for example, with this, because it's 5 year, we're going to use the middle value of the data, which is 3. So it means we're going to start at 3 when we start plotting our data. So we calculate the 5-year period by adding all the sales of 5 years. So in this instance, we start with the year. We calculate the average of the year, which is 3. That's where we're going to start. And we're going to calculate also the sales average, which are the sum of all the values and divide by how many there are and then that will be our average. So we know that our average for the year will be 3 and our sales will be 29.4. And we do that with all the tables. So we plotted average 3-year, which also has a 5-year moving average of 29.4, and we do the same. So we continue and do the next one, and we take 5 years, take the average of it, which will be 4, and then we take the average of from 40 till 48, add them together, divide by 5, we get 34.4. And you continue doing the same. You do for the next 5, you take the average, it will give you 5, and then we take the sum of all of them, divide by how many there are, and that will divide by 5, and that gives us 33.0. And you continue until you complete your moving average, and then you can plot your data. And this will show us the moving average of or the 5-year moving average of this sales data that we have. Then we can also plot it and see the pattern that arises from the data. And this we can compare what our actual annual data looked like and what our 5-year annual average looks like. So we can see after we smooth out the data, and we can see the pattern that arises, that it shows that over a period of time, our sales have been increasing. And that's how you do the moving average. Now, I'm going to give you an exercise. But before I give you an exercise, let's go back. Remember, you take the average or the middle value of the period, and then you start calculating the moving average by adding all the values in that moving average, summing them up, dividing by how many there are. Okay. Your exercise. A share trader has a policy of selling shares if the share price drops more than 1/3 of the purchase price. In January, the investor bought shares in Neutron, which is an electronic company, for 90 cents per share. The table below shows you the price of Neutron share at the end of each month. So those are the shares. It shows that in January it was 90, then now it dropped to 70 in July. Here they're asking you to calculate the 3-year period, three period moving average of the share price for May. And this is May. So you need to calculate the average for May for the 3-year. Do we have the answer? And Michelle says it is option 4. Is it the right? Are you answering the same question? Yeah, so it shows as you are answering the question I've just asked. So we're calculating the moving average for May. So if we're calculating the moving average for May for 3 periods, so it will be 78 plus 80 plus 74 divided by 3. And how much is that? 78 plus 80 plus 74 divide by 3 equals 77.333. Which is option number 2. And that's how you calculate the moving average. Any question? Any question? If there are no questions, then we can move on to doing the other method of smoothing technique, which is the exponential smoothing. So exponential smoothing, we use it for the short-term forecasting period. So it's not for longer term periods as well, because it can take you forever, because it's very intense. So what we do is we use the weighted moving average. But with statistical tools, it's easy to do these things, so you don't have to worry. One day you work for a company and they're asking you to do forecasting, and you think that you're going to calculate these things manually. No, there are statistical tools that does this. But in order for us to understand how the outputs work and what are the algorithm telling us, we need to understand the basics. So since we're using the weighted average, we can expect that the weights will decline exponentially, and most of the observation will be weighted. And then also, we should be able to plot it and see how the data looks after we've done the exponential smoothing. So since we're using the weight, we're going to name our weights W as our smoothing coefficient. And this is something that you choose. It's chosen subjectively. There's no mathematical proof to say this is how much you can put. So it's up to the researcher or the person who's doing the technique, how much, what weighting they will put on their data. So in your module, they will give you the weighting. You don't have to worry about that. They will tell you that your weighting is this much. Okay, so and the weighting needs to range between 0 and 1, because we're going to talk about 20% weighting or 80% weighting. So it means if you do 80% weighting, therefore it means the majority of the data will be from the 80%. If you say 20%, the majority of the data that you include in your average will come from certain value. So how do we do that? So the smaller the weight you give, the more smoothing it will be. The larger the weight, the more the less smoothing it will be. So it is always best to give it a smaller weighting. Okay. And this weight, if it's closer to 0, it will smooth out all the unwanted cyclical patterns that happens. Or also you will have like minor irregular components where there are lots of other errors that happens. And closer to 1, we can use it for forecasting. Because then it will tell you the real truth about it. So you don't, when you're doing forecasting, you don't even need to care about using the less weighting, because the more it has all those patterns, it tells you that you are actually using almost closer to the real data that you have. So that is why when you do forecasting, you want to use it the value closer to 1. So how do we calculate this weighting? So remember this, your first point of your data, that will be your exponential, in your exponential modeling, your first point will always be equals to the, or your exponential smoothing point for the first one will always correspond to the first value of your data. And that is that E1 is equals to Y1. So it means if my first value, if for example, we were doing that one with from year 1 until year 11, so it means from year 1, the value I see in year 1 will be my first value for my exponential smoothing. And then my next exponential smoothing, I will use the weighting. So I will say, what will my weighting be? So they can be, it can be 0.60 or 0.20. That will be my weighting. Then I'm going to multiply my weighting with my previous not my previous, but my current. My I will be the current value. So your I will include, or it will be your current value. So I will multiply my weighting with my current value. Then I will add 1 minus the weighting from my previous one. Remember the previous value that you got, your exponential value that you got. So it means if my exponential value, if I choose my weight, if I choose my weighting to be bigger, larger, let's say, if I choose my weighting to be 80%, so it means 80% of the data will come from my current value, and 20% of the data will be from the previous value. And that is why you will need to use the highest value when you do the forecasting, because then it means you are using the actual real current value for that month. Okay, and that is for the weighting. So if, for example, you're choosing less value for the weighting, then it means, let's say I choose 20%, then it means 20% will come from my current and 80% will come from the previous one. Or unless if I split it 50-50, so it means 50% of the contribution will come from the current and 50% will come from the previous one. And that's how exponential will work, depending on the type of weighting you want to use. So let's do this in real. So here, the weighting that was chosen was 0.20. We know that we have those period and we have our sales, our actual sale value. The next column is where we're going to calculate our previous weighting, because remember then our previous weighting will always be equals to the previous value that we have. In order for us to be able to calculate to substitute into the calculation, which is our E1. Now we can start doing the exponential. So remember, our E1, our first E1 is the same as our first Y1. So our Y1 was 1, so therefore that will be 1. Our next following one, it is our y2 multiplied by the weighting. Remember our weighting is 20, or maybe I should say wy2 plus 1 minus w times y1 for the second one. So our weighting is 0.2. Our y2 is 40. 1 minus y2 is 1 minus 0.2, which then becomes 0.8. And then we have our y1, which is 23. And when we solve this, it becomes 26.4. And that is 26.4. Then we move to the next one. So we take our 26.4, we put it on our next forecasting E1, because then this becomes our Y2, which is our E1 I1 minus 1. So we follow the same, 0.2, so we go W multiplied by Y3 multiply plus 1 minus W times Y2. And we complete the whole table and so forth. And then when you are done, you are able to smooth out your actual sales and create what we call a smooth sale using the smoothing technique. And by looking at the data, remember, this is the blue one represent our actual data, and the red one will represent your smoothing data, your smooth data. And if you notice, you will see that there is little or no fluctuations that you can see there, and the data is more smooth because we used a smaller weighting. If we used the bigger weighting, probably the trend would have looked somewhat like closer, like it will have mimicked, I'm not drawing it right, but it would have probably mimicked the blue one, but not totally, but it will still be smooth, but it might have looked like this. It might have, sorry, my hand is shaking, but it would have been smooth like that. So since we used the smaller weighting, and that's how it looks. Okay. With that, there is an exercise for you. Calculate an exponentially smooth series for the gold price. Smooth for the gold price time series of 1992. This is only for 1992 now. Using a smoothing coefficient of 0.8. So it means you're going to calculate by saying, remember we're calculating W, Y, YI plus 1 minus W I minus 1. So since we're calculating for 92, you will need to calculate, you will need to extend your table. Okay, I'll extend it this side because I ran out of space there. So you will extend your table, and then here you can create I minus 1, and here you can create the exponential. This formula, you can use it to calculate them. In order for you to get to 92, you need to do 90, 91, and 92 so that we can get 92. Okay, how far are we now? Okay, so let's do this. Let's see, you have the answer. You say it's number 2. Noliso says it's number 2. So let's see if it's number 2. Okay, so the first one we do is the 1991. So remember with 1990, we're going to take the price of our E1 as it is, and we can plot it there as our E1 as 384 anyway. So that will be that. Now, doing number 2, maybe I must change my colors so that let me change my color to blue. Let's use dark one. So this will be 384. And then we go and start doing, oh, actually not there. I'm putting it on the wrong side. Not at the E1, but here on our exponential. What am I writing now? 384. So now we need to calculate for the second one. So in order to calculate the second one, so if we go back to the table, to this, remember, that was our first one. So we need to calculate. We put the exponential smoothing will be the same as the original one. Now we need to do for line number 2. When we do line number 2, this, we represent it on line number 2. It stays the same because even after we calculate, it will go to number 3, like that. So, you know that is 384. So our previous value will be 384. So now we can calculate our exponential, our smoothing exponent. So our weighting, they told us it's 0.8. So it's 0.8 times the current one is 362 plus 1 minus 0.8 is 0.2 times 384. When we calculate all this, we get an answer of so 0.8 times 362 is 289.20 plus 0.2 times 384 is 76.80. And this will be 366.40. And this goes here, 366.40. And this will be 366.40. So we can now calculate the second one, our 0.8 times I1, which is 344. And 0.2 times our I1 minus 1, which is 366.40. And when we calculate this, we get 2 plus that 0.2 times 366 gives us 73. And that will be the answer that we're looking for. That would have gone there, 348.48. And that's how you do the smoothing, technique. Okay. Okay. So there is another one with on your own at your own time. They give you the weighted average of 0.2, and they're asking you to calculate for period number 4. So it means you need to calculate for 1, 2, 3 until you get to 4, so that you can see what your weighted average will be. Okay, so we can move on to how we do trend and seasonal effects. How do we calculate those? Oh, what are they? So with this, we're going to look at the 3 models, the linear trend, the nonlinear, and also the exponential trend model for forecasting. With the linear trend forecasting, so if you did STA1501, you would have done the linear regression. It is the same model. So we use the regression analysis trend line, which is your y hat is equals to B0, which is your intercept, plus your slope, which is B1x, where we use our x as our independent variable to predict what our y value will be. So with the linear trend, I'm not going to go in too much detail about it. Is if we want to predict, or we can plot this on a graph and it will look like this. And we know that the formula for the trend line will be completed like that, where it says this regression is given by 21.90, which is our y-intercept, where x is equals to 0. It means the average value for y will be equals to 21.905. However, for every 1 unit increase, which is our slope, then the data will increase by 9.5714. So it means if I put 1 on x, 21 will be added with 9.5 and create a new value for where x is equals to 1. So now we can use the same information and predict what the value of y will be. If we want to find out what our value of 6 for the 6th period will be, And by doing that, we just substitute where we see x with a 6, and we calculate and find that where y is equals, where x is equals to 6, the value will be equals to is equals to 79.33, and that will be the new point on the slope on the plane that we have here or on this plot. And there is your question. The trend equation is that y hat is equals to 1,200 plus 35t has been fitted to a time series for the industry workers. If t is equals to 1 for 1991, what will be the estimated number of working days lost during 2008? So what they want you to do is to substitute the value of t with the value of where 2001 will be. So what will be 2008? So you can say you can calculate it because you will say 1991, 1992, 1993, until you get to 2008. Remember, all these are linked to until you get to 2008. What will be t in 2008? And then once you found that t, so this is our t and this is our year. Once you find that period in 2008, which will be 17 at this point. That since we have our t as 17, we can just substitute into the formula. Y hat is equals to 1,200 minus 35 times 17. Which then is 35 times 17 is 595, and 1,200 minus 595 equals 600. And did I calculate right? 35 times 17. I did. And that is 1,200 minus 35 is, 1,200 minus 595 equals 605. Why am I not getting it right? 18, yes. Oh gosh, my calculations are wrong. Yes, my calculations are wrong. I said 17. We should add 1 again and it becomes 18. Oh, yes. So this will be 18 And 18 times 35 is 630. Oh, thank you very much. 1200 minus 630. And that gives us 570. And that is option number 5. There we go. And that is for the linear trend one. You will use this to forecast the new value that they will ask you to do. Okay. Now let's linear trends, which this can either be any of the other trends like exponential or so on. So with the nonlinear model, it will show a nonlinear trend. So it might go haphazardly and it might be constant or something like that. And this, it can also be one of the quadratic form that we have. And the formula to use will be y is equals to b0 plus b1x plus b2x squared plus the errors. And this will just give you, or we can also compare the adjusted R square, which is our coefficient of determination, and the standard error to see if this method improves the model or not. And we can also try other functional form which can best suit the data, because you plot you put the line based on the type of data that you have. If your data looks exponential, you're going to plot an exponential. If it looks like a quadratic form, you're going to plot your data as a quadratic. If it's a trend, you're going to plot it as a linear trend line. So another method, which is an exponential, if it's not quadratic, it will be an exponential one. And with an exponential, we use the formula y is equals to b0 times b1. So it's your intercept times your slope to the power of your x times your margin of errors. Okay, and then when we transform this nonlinear trend, it becomes a logit regression line or a logit linear line, where it will be your log of your y hat is equals to the log of b0 plus x times the log of b1 times the log of the error. And this is what we call an exponential trend forecasting equation, which is the log of the exponential of the linear function, which we can also write it as a linear equation for the forecasting. Okay, so now let's move into looking at, unless if there is anybody with a question, we're going to move into our last segment, which is forecasting. So how do we then do this? What is the forecasting? For forecasting, we will have to choose the model like we do with the time series and the trends, where we have different types of models. Also, you will have to see which model you want to use for your forecasting, whether you want to use the trends or so forth. But some of the models, they perform better than the other. But then how do we test if the model that we want to use, those models, the linear one, the moving average one, the quadratic form one, the logit or your exponential one, which one should you use? And this is where you need to choose metrics or measures that can evaluate which model performs better for forecasting. And to do that, we're going to use what we call, there are two methods that we can use. So we're going to use our residual analysis to look at the pattern and the trends, so which are your errors. Remember those errors. And we're going to use those errors to see or measure the magnitude of those residual errors by using their differences of this, the square differences of those errors. And we can also use what we call the absolute differences, which we will use the absolute measure or absolute average deviation to measure the performance of each of those models as well. And lastly, we also want to use the simplest form of all models, because you don't want to use a complicated model that you are unable also to explain. So in terms of what I'm saying, when we look at the residuals, remember the residuals are just the errors that can be accounted for or not accounted for, but most of the time they cannot be accounted for. So for example, here we're looking at the type of errors that can be there. So if we look at the first error, these are just random errors. If we look at the second errors, we can see that they form part of some cyclical effects, which we can also say the cyclical effects are not accounted for in this in that analysis or this model that we used. It came with the cyclical effect. Or the errors can be a trend, which also it means that the errors that we got form part of a trend line. And also you can get where it is a seasonal effect that you can they cannot be accounted for. Remember, those are just your errors. And if by analyzing these errors can also assist in making sure that we choose the best model that will fit your forecasting model. So measuring the errors, we use those to choose the model that gives the smallest errors as possible. And the first one measure that we can use is the sum square errors, which we calculate by adding all your estimated values minus your forecasted value. So your this is your actual minus your forecasted values. So it means once you have your actual value and you calculated your estimated values, you can subtract one from the other and square the answer in order for you to find the difference in those errors. And the smallest one, the model with the smallest error, sum square errors, will be the best model. And this model is also sensitive to outliers. So if your data contains bigger values that are away from the rest of the other values, it's got highest outliers, your sum square measure error will also be affected by that calculations, because then you will also have the estimated values that are way too far that will skew your data. So it's very sensitive to outliers. The other measure that we can use to choose the best model is what we call the mean absolute deviation. And with the mean absolute deviation, we try to convert everything. If it was going to be a negative value, we're going to make sure that it becomes positive. And we also take the average of those values because this is your mean, meaning the average. So this model is less sensitive to extreme layers. So, and then it means if you have extreme layers, then your mean absolute deviation will be the best method to use to check whether that model that you are using is the best model to do your forecasting. So now we have two measures that we can use to check whether the model that we're going to use is the best model to forecast your data. Okay. Okay, so now let's look at an example. Look at an example of calculating the mean absolute deviation. So we are given the data, we are told what the actual is and what the forecasted value was. So this is our FT and this is our YT. So remember the formula for MED? The formula for MED is the sum of your absolute value of your Y minus your forecasted value divided by N. Know what the formula is? Now we can calculate the MED. Calculating the MED, we say our actual is 57. So you will say 57 minus 63, but this is absolute, so it means the answer you get here will always be positive, plus 60 minus 72, plus 70 minus 86, plus 75 plus 71, plus 70 minus 60. So that will give us, take my calculator and calculate quickly. This is 6. Oh, sorry, and I forgot. We're going to divide this by how many there are? There are 5, so we divide this by 5. So this is 6 plus, and this is 12, and okay, so 80 minus, I mean, this is 16 plus 2. And plus 10, divide by 5. So this will be 6 plus 12 plus 16 plus 2 plus 10 equals 46 divided by 5. And this gives us 9.2. I might have calculated something wrong somewhere. Let's see. 63 minus 57. Please double check for me if there is something that I calculated wrong. 60 minus 72 is 12. Since everything will be positive. And 70 minus 86 is 16. Sorry?
The 75 minus 71 is 4, not 2.
Oh, I have it here as 73. Oh, sorry, my bad. I can't even see my handwriting. Sorry. So that is 75. Yes, I can see that. That is 4. I thought as much. So it will be 48. 48 divided by 5. It's 9.6. Oh, yeah. And that is 9.6. And that's how you will calculate mean, which is mean absolute deviation. Next exercise is, or example, is to find or calculate the sum square errors or the sum square for forecast error, which is SSE. And we know that we are given our y hat and our y, which are our interest rates, and the estimated interest rate. And we know the formula is that, and it says it is the difference squared. So it's the sum of the difference squared. I'm not going to write it there. I'm going to just do it on here. I'll write the answers from here. So this will be your y hat minus ft squared. So this will be, so you must also calculate with me so that if there is any calculation that I do wrong, you can correct me. My 10.46 minus 10.81 equals, remember on this one, it's not absolute, so we're going to square the answer. So because I'm using my financial calculator, I'll press second function and I'll press the dot button and it will square my answer and I have 0.12. And move on to the next one, 10.86 minus 10.85 equals second function dot equal set up decimal. I'm going to change my decimals to 4 because it doesn't seem like it's working. 86 minus 10.85 equals 0.1, and I square that answer and I get 0.001. Do you also get 0.001? And I'm going to start number 1, go back to number 1 as well, because I need to leave my answer in 4 decimals. It's 0.1225. 0.1225. Okay, so we can move on to the next one, which is 12.07 minus 10.9 equals and square the answer. 1.3689. 1.3689. 9.97 minus 10.95 equals square the answer. 0.96. 0.9604. Then the last one, 11.14 minus 10.99 equals 0.15. 0.1500. Okay, so since it's the sum, I must add all of them up. So I'm going to start from the bottom, go up. 0.15 because I already had it on my calculator. Then I go 0.9604 plus 1.3689 plus 0.001 01 plus 0.1225 equals 'kay. So our answer is 2. I still don't have the answer. 0.6019. Where did I go wrong? Did you calculate? Check your answers as well. See if there is somewhere where I calculated it all wrong. I will start again. 10.46 minus 10.81 squared. It's 0.1225. 10.86 minus 10.85. Square the answer. 0.001. 12.07 minus 10.9. 1.3689. 1.3689. 9.97 minus 10.95 squared. 0.9604. 11.14 minus 10.99 equals 0.15. I give up. I got the same answer. So let's see. Maybe it's my calculator. So what do you get? Period for should be 0.025. Which one? Option 3. Michelle, which one? Is there something that I am calculating that is wrong? Period 5 should be 0.025.
Yes.
Where? Which one?
In 1991. Year
For
1991.
1991. It is
Yes.
11.14 minus 10.99 equals, square the answer, equal. Oh, yes. What was I getting different answers? So 0.0225. So the last one should be 0.0225. Yes, okay. And if you add all of them up, then the answer will be option number 3. So 0.1225 plus 0.001 plus 1.3689 plus 0.9604 plus 0.0225 equals 2.4744. Okay, so we won't have enough time, but this was supposed to be your exercise. You can try and do it. You don't have to calculate anything. All you just need to look at is they give you model number 1 and model number 2. And remember, the best measure to choose the best model, because now we need to choose which model between the two is the best model that we can use, or it will be the best fit model for the data. So remember, you look at the measure, which will be the sum square measures. We're always going to choose the best model by looking at the smallest value of your SSE or your MED. Based on the information that I just said, look at the information you have and choose which of this regression model provide the best fit for the data. So which model, which question will be the correct one? Number 1 says model 1 is better than model 2. Number 2 says model 2 is better than model 1. Number 3 says the two models are the same. Number 3 says none of the two models, no one among the two models best fit the data. And 5 says we need more information. So if we take our SSE, because they give it to us as part of the table to confuse you. So this one comes from model 1 and this one comes from model 2. Okay. So you see, you have number 1 is correct. Yes, because model 1 has the SSE of 4.95 and model 2 will have an SSE of 593.25, which makes model 1 the best model to best feed the data. And with that concludes STA1502 content. So you should be ready to write your exams because most of the exercises that we just did actually for the entire module are based on your past exam papers. So it means we did some sort of your exam revision while we were busy going through the content. What's coming next will be next week. We're going to, I think next week, Thursday will be the last, next week, Tuesday will be the last time I see you when we do exam preparation. So we'll go through one exam paper and then just go through all the questions. And also answer questions that you are uncertain about, that you still need help with, or some of the concepts that you're still grappling with, because your exam is on the 7th, I guess, if I can still remember well. So just to prepare you for the exam. And that concludes today's session. Just to wrap up, we looked at time series, we looked at the different models or techniques of time series, moving average and an exponential, and then we looked at the seasonal trends, and then we went and looked at the models, or choosing the best model for your forecasting by either looking at the two measures, error measures, which are your sum square errors of your forecast and your mean absolute deviation measure. And those measures, we said, if you look at them to choose the best fit model, you will always choose the one with the measure that has the less or smaller measures. And with that, we are good. Thank you for coming through. Enjoy the rest of the day and see you next week, Tuesday, for the last time online. Thank you, guys.